Okay, welcome, Magnet Pre-Calculus. This will be week 3 of your school year for 2019 and 2020. We are going to look at tests for convergence and divergence of an infinite series. Students usually do not like this topic. I'm going to look for some other videos on YouTube for each of the tests. But I'll be here for office hours if you have any questions. Okay, so first of all, to understand what we're even talking about, we need to talk about the definitions for converge and diverge. So converge means to meet or come together. You can determine a conclusion. Diverge, obviously, would be the opposite. We're going to say it means to move away. Or to extend in different ways. And in our case, to infinity or negative infinity. Many quantities that arise in applications cannot be computed exactly. For example, pi, we say 3.14, but we know it's an irrational number that goes on forever. Euler's number, E, 2.718 we use, but it actually is another irrational number that goes on forever. But we can express these quantities as infinite sums or infinite series. Okay, so basically we're going to be given some sort of sigma notation. And you'll see that there's an infinity at the top that defines it as an infinite series. But we're going to look at the nth partial sum to determine if the series converges or diverges. So the sigma automatically means it's a series and that we want to find the sum. So a partial sum is going to be not going to infinity, but just adding a certain number of terms. So this is showing we're adding the first term to the second term to the third term, and we're going to keep going with that pattern until some designated nth term. Okay, but we're not going to try and continue to infinity. We're going to stop it at some point. That's what makes it a partial sum. So if the sequence of partial sums S sub n converges to some number, then we say the whole series converges, even though the whole series really goes to infinity. The limit of the sum is called the sum of the series. If the sum to this nth partial sum diverges, then we would say the infinite series diverges. So we're going to look at this partial sum, make a conclusion, and apply that to the infinite series. So we're going to start out with the two easiest tests, which is going to apply to last week's review of sequences in series. So here is an infinite series. Again, the fact that we used a sigma means it's series, and that infinity on top makes it an infinite series. And the expression is 1 over 2 to the n. That designates what type of series or pattern it is. But if you substitute 1 in for n, you get the first term of 1/2. It's a series, so we're going to do pluses. If we substitute 2 in, we get the second term 1/4. If we substitute 3 in, we get the third term 1 over 8. The fourth term is 1/16. And this pattern would continue to keep going until whatever our nth partial sum we needed that to go to. And so this would be 1 over 2 to whatever that place that we wanted to go to is. So we can write this as sub n as 1/2 plus 1/4 plus 1/8 plus 1/16, and till whatever we want to decide is going to conclude our partial sum 1 over 2 to the n. So if we're looking at the sums here, the sum of just the first term, so that's a partial sum of just the first term, and so the sum obviously would just be whatever the first term is. The sum of the first two terms would be 1/2 plus 1/4. You would get a common denominator, blah, 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 but you would get 3/4. The sum of the first three terms would be 1/2 plus 1/4 plus 1/8. And getting a common denominator and adding those fractions together, you get 7/8. There's a pattern that's developing. The sum of the first four terms, you get 15 over 16. So so you could keep going for as long as you want to, but what you should notice is that every time we increase the number of terms in our partial sum, we get a fraction, but that fraction is just growing closer and closer to 1. As the difference between the numerator and the denominator is 1 every time, but the value of the numerator and denominator is increasing, then, so this is 0.5, 0.75, and if you work out these decimals, you'll see the decimals are getting closer and closer to 1. And so as you keep adding another term onto the end, you'll just see the next thing. If I went sum of the first 5 terms, then the denominator would be 32, and my sum would be 31 over 32. Okay, so we can see this pattern here, that it's getting closer to 1. Now, we've already seen this pattern before. This is an example of a geometric series. We know that because we can determine that there is a common ratio. If you multiply by 1/2 each time, you will get from any term to the next term. So it's a geometric series if the pattern has a common ratio, and this does. It has a common ratio of 1/2. And so when we did the review last week, there was an infinite geometric series, and there was a formula that goes along with that. But before we applied the formula, first we had to look at the value of the common ratio. And if the absolute value of the common ratio is less than 1, then we can proceed on to the formula, which is the sum is the first term divided by 1 minus the common ratio. The first term was 1/2, the common ratio is 1/2, and when you work that out, you get that the sum is equal to 1. So because we determined it was geometric and the common ratio had an absolute value less than 1, then we would say this series converges, apply the formula, and it converges to a value of 1. Okay? So let's look at the official rule and its application. So if the absolute value of r is less than 1, use our formula to get the sum to which the series converges. So if the absolute value of r is less than 1, this series converges. If the absolute value of r is less than or equal to 1, then use no formula. Then the series diverges. We would just stop with that it's geometric, the common ratio has an absolute value less than or equal to 1, and therefore it diverges. There is no sum. This kind of series is going to continue to grow or continue to get smaller, so it is going to go to either positive infinity or negative infinity, which is how you know it diverges. So let's look at some examples. All right, so example number 1, this is actually not geometric, right? You're not multiplying by the same thing each time. There is no one value that you could multiply each time to get from one term to the next. This, though, is arithmetic. So arithmetic, we know because we can see that there is a common difference because we are adding 2 each time. So if it's arithmetic, you don't have really any work to do after you determine it's arithmetic because there's a common difference. Arithmetic series always diverge. So after you say that it's arithmetic and a common difference, then you can just say diverge. Okay, that's it. For number 2, there is a common ratio here. So we can say that this is geometric because there's a common ratio of 2, multiplying by 2 each time. Because the common ratio is greater than or equal to 1, there is no formula, there is no sum, we just say it diverges. For number 3, this is back to arithmetic. There is a common difference. It is going down by 5 each time, so the common difference is -5. And once you've stated that it's arithmetic and what the common difference is, you want to do both of those things because you want to make sure you can determine a common difference to be sure that you're right that it's arithmetic. But once you've stated both of those things, you just conclude that it diverges. For number 4, so this one is a little less specific. It's written in that infinite series format. If you want to write out a couple terms, you could substitute in 0 and get the first term, and then substitute in 1 and get the second term, and substitute 2 and get the third term, as many times as you wanted to get to see what the pattern is. But if it's exponential like this, then it's a good chance it's geometric. And the base of the exponent is your common ratio. So it's geometric. The base of the exponent is my common ratio. The absolute value of my common ratio is less than 1. So we can determine that there is a sum. It converges to, we're going to do a sub 1. Again, if you plug in the bottom number, you get the first term. 1 minus r. So it converges to a sum of 10. Okay, so because of all this, we can say that all infinite arithmetic series always diverge. Okay, so when you're starting out anything with convergence and divergence, it's kind of like a protocol just to make your life easier. So the first thing that you want to do is look at what you're given. If you need a couple terms written out to determine what the pattern is, then just plug in the bottom number, plug in, keep going consecutively to generate maybe the first 3 terms, determine if there's a common difference. If there is, it's arithmetic, and you can say it diverges. If there's a common ratio, then it's geometric, and do the test on the common ratio to see if the absolute value is greater than or equal to 1 and say it diverges, or that the common ratio has an absolute value less than 1. And then you apply our formula, a sub 1 over 1 minus r, to say it converges to that particular sum. The only type of infinite series where we're actually going to find a sum to which it converges is geometric. Every other type that converges, we're just going to stop with saying it converges. Okay, but that's the first thing you want to do. Okay, check to see if it's arithmetic or geometric. If it's arithmetic, say it converges, diverges. If it's geometric, apply your test for the common ratio and either say it diverges or it converges, and then you have to use the formula to find the sum. Okay. So if you've done that and it's not arithmetic or geometric, the next thing you should check for is the end term for divergence. So again, we have a sigma notation. So we know it's a series with an infinity. So that makes it an infinite series. And a sub n is just representing whatever expression is next to your sigma notation. That expression is how you can determine if the pattern is arithmetic or geometric. So we're going to assume that it is neither here. And that's why we're using a different test. So we have a limit as n goes to infinity. So we've been over that, rule 1, rule 2, rule 3. If the limit to infinity of this expression next to the sigma is equal to 0, okay, then if the infinite series converges, then the limit to infinity will be 0. Okay, because this is true, it's contrapositive, not converse, is also true. So you had, back from geometry, you had your statement, and then you had inverse, converse, contrapositive, you had all those. So if it's a converse, that was where you wrote it backwards, and then you had inverse where it was negated, and then you have the contrapositive, which is backwards and negated. So we're going to take this statement right here, and we're going to write it backwards, but also negate it. So if the limit to infinity does not equal 0, we're going to write that first and negate it. Then the infinite series diverges. So we wrote it backwards. This statement is written backwards and negated. So this is going to be our term for our divergence test right here. Okay, we're going to see if the limit to infinity is not 0, a rule 2 or rule 3. If so, we can conclude that our infinite series divergence. This is just a divergence test. So if the limit to infinity doesn't equal 0, then you can say it diverges. If the limit to infinity does equal 0, you cannot conclude that it converges. You just have to pick a different test. Okay, so it's just a test to conclude with divergence. Okay, so here we've been given the first 3 terms of the infinite series, but then they've told us what the pattern is. And so that's really what we're going to look at. This right here is our a sub n that is mentioned up here in our rule. Okay, so we are going to apply a limit to infinity to this expression right here. The limit as n goes to infinity of n over 3n minus 1. Okay, rule 1, rule 2, rule 3. This is a rule 2 because the degree of the numerator is the same as the degree of the denominator. Okay, they're both of the first degree. So the limit to infinity would be, you just take this and reduce 1/3. Well, last time I checked, 1/3 was not equal to 0. And so if we go back up here, if the limit to infinity does not equal 0, then our infinite series diverges. And so we conclude that this diverges. Okay, example number 8. That's a little trickier just because we haven't spent much time talking about factorial. You should have seen factorials before in Mag Advanced Algebra with permutations and combinations. We may have talked about them a little bit earlier in the year, but basically the way that you want to view these factorials, it's not really a degree, but this is a sub n. Sorry if you can hear the planes. The limit as n goes to infinity of n factorial over 2n factorial plus 1. So even though it's not a degree, we kind of want to apply that same rule that we have n factorial over 2n factorial, and we're going to treat this as a rule number 2, where we're going to pretend like that's the same as having the same degree, and we're going to just look at that part and reduce it to 1/2. But again, that limit to infinity is not equal to 0. So we can again conclude that it diverges. So as long as you're good with your limit to infinity rules, this is a pretty easy test to check to see if you can use it. So let's look at number 9. So this right here is my a sub n. So I'm going to do a limit as n goes to infinity of 1 over n. Well, this is a rule number 1. The degree of the numerator is 0 and the degree of the denominator is 1. So rule number 1 says the degree of the numerator is less than the degree of the denominator. So the limit to infinity of a rule number 1 is 0. So what we've determined here is not that this series converges. This is just the test fails. So it's inconclusive. And you have to use another test. Okay, so we can't say that because it equals 0, this doesn't apply. We can't say that it converges. We have to know it converges, and that will mean that the limit to infinity is 0. But we cannot make the conclusion of convergence. And we're going to see that come up again in a test that we could use. So again, these are kind of in the order that you want to apply them. First, check to see if it's arithmetic, geometric. If it's not, then in your head even, you can just look at that expression, think about, is it a limit to infinity rule 2 or rule 3? If it is, you'll be able to use this test. If it's a limit to infinity rule 1, then just move on to a different test. You don't have to write out, you don't have to go through the test. You can just in your head know that's a limit to infinity rule 1. This test isn't going to be what I need. So the next test is the p-series test. We have an infinite series, and the expression is 1 over n to the p power. Only real rule is that that power has to be a real number. That's what it means by a real constant. And the power has to be greater than 1. It doesn't have to be an integer, but it has to be a real number greater than 1. If that's the case, the series converges. If the power is a real number less than or equal to 1, the series will diverge. Now, what's important for this is it must look just like this. 1 over n to the p power, where p is a real number. Otherwise, this is not the test. Okay. All right, so first example, the expression written next to our infinite series is 1 over n squared. Okay, so if we're trying to make it look like 1 over n to some power, we have that 1 over n to some power. In that case, the power is 2. So the test is pretty easy. Is that power greater than 1, or is the power less than or equal to 1? Well, in this case, that power 2 is greater than 1, and that gives us a conclusion of convergence. That's it, done. For number 11, remember, it's got to look like 1 over n to some power. Well, that's not what this looks like, but n times the square root of n is really n to the first times n to the 1/2 power. That means the same thing. And if the bases are the same and you're multiplying, you can add your exponents, and 1 plus 1/2 is 3/2. So if I rewrite the expression they gave me using what I know about rational exponents with conversion from radicals and exponent rules, this is the same thing as 1 over n to the 3/2. And so it's 1 over n to some power, where the power is a real number. The power is 3/2. Okay, well, 3/2 is greater than 1. So this also converges. Example number 12. So we just saw that in number 9. In number 9, we tried the nth term for divergence test, and because the limit to infinity was equal to 0, we were like, we can't say, we got to try a different test. So the test we're going to use here is the p-series test. So that is the same as 1 over n to the first power. Okay, obviously the first power is implied, so that makes the power equal to 1. Well, that is less than or equal to 1. Obviously, it's equal to 1. And if p is less than or equal to 1, the series diverges. So back when we were looking at it in number 9, kind of thinking, okay, well, if the limit to infinity is 0, how come we can't just say it converges? Well, now you know, because this test was inconclusive, so we were kind of thinking that must mean that it probably was going to turn out to be converges. But when we applied the p-series test, then what we determined is actually did diverge, even though the nth term for divergence test didn't work for us. Okay. We're going to talk about one more test today. And next week, we will finish up with the other test. So this is the last one, the alternating series test. So we have some expression that's greater than 0. And the alternating series test, it'll be pretty easy to determine because you're going to see this part of -1 raised to some power. It could be -1 to the n power or -1 to the n plus 1 power. It could be -1 to the n minus 1 power. The most important thing is you're going to have this base of -1 to this exponent that has n in it. And then there'll be some other expression right next to it. Okay, so if you see this -1 to the power, then alternating series test is going to be what you need. So this is actually going to tell us if it converges, but we have 2 conditions to run through. The first is the limit to infinity has to be 0. So the limit to infinity will be 0 if it's a rule 1. Now notice that you have these expressions right here, but when you ran this test, we did not use the -1 to the power part. So when we see that it's alternating because -1 raised to some power is going to produce alternating values of -1 and +1. That's why it's called alternating. Okay, this part of it will make the terms go back and forth between positive and negative. But when we run these condition tests, we're not using that. We're just using the rest of it. That's important that you're throwing out this part that made it alternating when we actually go through the conditions. So we're just using this part. This is our a sub n right here, okay? So it's this part that makes it alternating, and then the rest of it is what makes our test work. So our first test is limit to infinity. So the limit to infinity of 1 over n. Well, we've just been over that a couple times. That's rule 1, because the degree of the numerator is less than the degree of the denominator. So the limit to infinity is 0. That's our first condition. So now I have to move on to the second condition. If the first condition is not met, then stop. This isn't the test you should be using. So then we're going to go to our second condition. And that says if that expression a sub n plus 1 consistently is less than or equal to a sub n, no matter what the value of n is, then that condition is met, and we can go back and say it converges. So what that means is I have some expression, and I would say like the fourth term is consistently less than or equal to the third term. The 10th term is consistently less than or equal to the 9th term. That's kind of what that is saying. So here, remember, my a sub n is 1 over n. And so my a sub n plus 1, okay, instead of n, I have n plus 1. Is that consistently less than or equal to 1 over n? Well, you could just say right here, yes, that is true, because if our numerators are the same and this denominator is always going to be bigger than this denominator by a value of 1, if the numerators match but the denominator is bigger, then that overall value is always going to be smaller. So you could know right here that yes, this condition is met. But let's try it for a couple of numbers. So let's say here it said that n started at 1. So you're allowed to start at 1 and go up from there. But let's just say we did, okay, so n equals 1. So for n equals 1, it would be 1 over 1 plus 1, which is 2, less than or equal to 1 over 1. That's true. 1/2 is less than or equal to 1. For n equals 2, it would be 1 over 2 plus 1, less than or equal to 1 over 2. And yes, 1/3 is in fact less than or equal to 1/2. 0.3 repeating is less than 0.5. Let's try it one more time. If n equals 3, so again, we're putting a 3 here, so that would be 1/4 less than or equal to 1/3. That's 0.25 less than or equal to 0.3 repeating. So you can see that as we move up with our value of n, every time we're getting a situation where the a sub n plus 1 situation stays less than or equal to the a sub n we were given. So in fact, this condition is met, and if both conditions are met, then you can say it converges. Let's try that with something that's a little more complicated. So for number 14, well, it's missing. You said that it had to have that -1 to a power situation. It doesn't have that. But we can rewrite this where we can pull out the negative part of that base of -2. And the power was n minus 1, so I'm going to be consistent there, times +2 to the n minus 1. So I can break this apart into a -1 times a +2 to the same power. That means the same thing. Okay. And it really doesn't matter if this -1 to a power is on the numerator or the denominator, because all it does is make the value of each term alternate between positive and negative. And in a fraction, that doesn't really matter if your negative is in the numerator or denominator, it's still going to give your overall fraction value either positive or negative. So your a sub n is just this portion of it. Okay, that's your a sub n. So step 1, let's do a limit as n goes to infinity of n over 2 to the n minus 1. Well, we didn't see a lot of these when we were doing a limit to infinity, just a few examples, but it doesn't really fit in your rule 1, rule 2, rule 3 scenario, because we have a degree of 1 on the numerator, but we don't have a degree in the denominator. So instead, in this situation, we want to look at the types of functions. The numerator is a linear function. It's the identity function, just like y equals n. And we have an exponential function in the denominator. Well, a linear function grows slower than an exponential function, right? The growth of a linear function is constant, whereas exponential keeps getting bigger and bigger, faster and faster. So what this represents is slower growth over faster growth. And in that case, your limit to infinity does, in fact, equal 0. So anytime you can't use the degree rules and you have a slower growing function divided by a faster growing function, then your limit to infinity will be 0. If it's a faster growing function over slower growing function, then the limit is going to be infinity or negative infinity. And this isn't the test for you because it's not going to meet our two conditions. So then let's move on. Now that we know our first condition is met, let's move on to the second condition. So a sub n plus 1 less than or equal to a sub n. So a sub n plus 1, we would add a 1 to each n that we see in this expression right here. So our numerator is going to become n plus 1. And our denominator, we're going to add 1 to that n. But when we add 1 to n minus 1, then we have n plus 1 minus 1, which just ends up being n. Okay? And is that, in fact, less than or equal to n over 2n minus 1 for all values of n? So again, let's just try to see if we plug in some numbers, if that condition is met. So go back up here. It says that you can start at n equals 1. Let's start with n equals 2 this time. As long as we go something bigger than or equal to this number, we're good. So let's just do 2. So if we do 2 plus 1 over 2 squared, that's 3/4. And this would be 2, and 2 raised to the 2 minus 1, 2 to the first is 2. Well, 3/4 is less than or equal to 1. Let's try n equals 3. So 3 plus 1 is 4. 2 cubed is 8. Is that less than or equal to 3? And then 2 to the 3 minus 1 is 2 squared. Well, this is 1/2 is less than or equal to 3/4. That's true. So you do it a couple times, at least 2, I would think. You can keep going if you want to do it another time, but this condition is also met. So again, we can say that this alternating series converges. So your assignment for this week, there's one document called Series 1 that has 20 questions, but the first 10 would use either arithmetic, geometric, nth term for divergence, p-series, or the alternating series test. And 11 through 20 use the test that we haven't gone over yet. They're for next week. So just a reminder, make your life easier. First thing you want to check is the pattern arithmetic. If you can't tell just by looking at your sigma notation, then generate a few terms and see if there is a common difference. If it's arithmetic, it converges. If it's geometric, then there would be a common ratio. You see if the absolute value of the common ratio is less than or equal to 1. If yes, it converges. You use the formula to find the sum. If the absolute value of the common ratio is greater than or equal to 1, it diverges and you're done. If it's not arithmetic or geometric, see if you can use the nth term for divergence test, which just would be a limit to infinity, rule 2 or rule 3. If that is the case, you can say that it diverges. If it would be a limit to infinity, rule 1, then that is not the test for you. You want to try p-series. Make sure it's 1 over n to some real number power, and see if that power is either greater than 1 for convergence or less than or equal to 1 for divergence. And lastly, the alternating series test, which should be pretty easy to spot because you'll see this -1 to the power that has n in it, which is why it's alternating. That part of your expression alternates the series between positive and negative.